Hello guys, how are you doing? So I'm going to solve this problem using virtual work. The problem is asking to calculate the deflection at the point C. So let's start working that out and see how it works. First thing, I always like to do that. So remember what is the philosophy of virtual work, and basically what it is that the external work has to be equal to the internal work. The external work is going to be given by uh, an external force, virtual force, which by convenience is given a value of 1 multiplied by the displacement or rotation in the direction that we are looking for. Uh, of course, in this case, we're not talking about the rotation, we're talking about the deflection. And that has to be equal to the internal work. And the internal work is just going to be the summation of all of those internal forces. For the case of the truss, is going to be only axial forces multiplied by the deformation, which is this one. So this is the deformation. Remember, deformation is PL over AE, and the internal normal forces, I'm just calling them normal here instead of axial, because sometimes get confused the A with the area. So I don't want that to happen. So that's why I'm calling them axial forces. First step for doing this is solving the real truss. How are we going to solve the real truss? Depends on you. You can start from this joint if you want to, because there's only two unknowns, and then you can move here. Look at that. If you look to this joint, immediately you can see that this force is 25. Just by doing the analysis over there, you can come to this joint here and calculate this and that. But let's say that you don't see that. Let's say that you start doing reactions. So I'm going to start calculating reactions. The moment is here in this direction. This is gonna be one force in that way, one force in that way. Reaction, I mean, dx, dy, and this is gonna be in the other direction, and this is gonna be ax in that way. There's no x, y, because this is a roller. So let's start by doing summation of forces in y. If we do summation of forces in y, dy is going to be equal to 25 plus 25, 50 keep. Then we can do summation of moments, whatever you want to do it. We can do summation of moments at A if you want to. The moment here. So we have dx multiplied by 15, 15 times dx. And then you have minus 25 times 20, minus 25 times 40 equals 0. And from here you can solve for dx, which is going to be equal to 100 keep. This is 500, this is 1000, 1500 divided by 15, 100 keep. And now by doing summation of forces in x equals 0, you get that ax is going to be equal to 100 keep also. Now once you have that, if you come to this joint, you don't even have to do the analysis of the joint per se, but you can. I mean, you can go to the joint D, and you can put your joint D there, D, and then you can put this force here, which is dx 100, and then you can put this force here, the force coming from the reaction in dy, which is 100, and I'm gonna put the bar here also. This is the bar dA, which obviously goes in this direction, and then you have the bar dE in this direction. So from here you can see that dE is going to be equal to 100 and dA is going to be equal to, put here 100, this is not 100, this is 50. 50, so dA is going to be equal to 50 also here. I know that some of you were yelling at me because I did that, but I'm not going to erase that thing over there. I'm used to be yelled at, so no problem. So this is going to be dy, and you know dy is going to be and dA, I'm sorry, dA is going to be acting in this direction, and it's going to be 50. This is going to be dE, which is going to be 100 in that direction also. Meaning, if this is 50, of course you have 50 here also, in that way, and this is 25. So now we can move to, let's say this joint A, if you want to. So let's move to that joint A here. AX 100, this is 50, which is the bar DA here, and then you have this, which is AE, I'm sorry, and this is AB here. What direction goes this is up to you, but you can see that the diagonal, which is this one, is the only one in the vertical direction countering this, so it has to be like that in compression. And the direction for this one, depending on this value, it will go to the right or to the left. I think that it's gonna go to the left, but in compression, but it doesn't matter. You know, the science is gonna tell you that. And then you have this angle here, and that angle here, or you have this triangle here also. You can use the triangle, it's easier. Not easier, it's the same thing. This is 3, 4, 5, because this is 15, 4, 15, 20. Dividing that by 5, this is 3, 4, this is going to be 5. Or you can calculate the angle if you want to calculate the angle also. First thing first, summation of forces in Y equals 0. If you do that, then you have 50 minus 3/5 AE equals 0. There's nothing else there. So AE is going to be 250 divided by 3, which is 83.3, periodic, repeated, keep. And remember, that is in compression. I'm going to put that in case I forget, but it's given here. So I like to do this also, putting it there. And immediately after I know that, I'm going to do that there, and I'm going to do this here. And I know this is 100, and I know this one here is 83.3, periodic. And now we can do summation of forces in X equals 0. If we do summation of forces in X equals 0, I have 100 minus 4/5 AE minus AB equals 0. And then you can solve for AB. And AB is going to be equal to 33.3 periodic kips. In compression also, because I assume it was in compression. So now we have this one also here, which is this and that, 33.3. This force here has to be equal to that, so this is also 33.3, as well as this one. And this one is 25, because this is 25. And the only missing force here is this one, which has to go in this direction. So if I go to the joint C, you have the 33.3, you have the one here, which is the one that I'm looking for, CE or EC, and then you have this 25 here, and then of course, once again, you have the angle 345 here. So CE or EC, which is the same thing, times 4/5, if you do summation in X, 4/5 minus plus 33.3 equals 0. So CE is going to be equal to 41.6. And you can do also as well summation of forces in Y, just to verify this, and then you can say that 3/5 CE minus 25 equals 0, and then you're gonna get that CE is gonna be equal to 125 divided by 3, which is exactly 41.6 kip. So now we have all the forces in the real structure. Next step, we're gonna get those forces now, and we're gonna calculate those forces for the virtual structure. What do I mean by the virtual structure? Well, the virtual structure, the geometry is gonna be identical to the real structure, identical, same thing, I'm just using the same page. However, the only difference is that you are going to put these loads are not gonna be there, and this load is not gonna be there also. So the only thing that you have to do in the virtual structure is placing a virtual load or a virtual moment, of course not in the case of trusses, because obviously you cannot have moment in joints, at joints, but you have to place, in this case, if we are looking for a vertical deflection at point C, then you're going to put a virtual load, any magnitude, any value, but if you use one is easier, at the joint C. And then this will be the second step, which is calculating or working with the virtual structure. I'm gonna put here in the first step, I just put the number, but let's put here the real structure. So basically we do statics, once again, in the real structure, and we do again statics in the virtual structure and calculate every single one of the forces. Now, if this force doesn't exist, this is a zero force member here, zero force member here. If this is 1, in this case, then there's only one force, meaning the reaction for dy is gonna be equal 1. You can do it, I mean, but I know this is gonna be 1. You can do summation of forces in y equals 0. So dy equals 1. So, but if this is 1, then this force here is gonna be also 1, meaning this force here is gonna be also 1 by doing summation of forces in y in that particular joint. Now, you're gonna have also dx here and ax here. The reason I put these directions is because I know that this force is gonna generate an overall moment in this direction, so this couple of forces have to be in the opposite direction in order to counter for that moment. So I can do the same thing. I can calculate summation of forces in y. I can calculate summation of moments at A equals 0. I can start from this joint and I don't calculate reactions. This is actually I would start from here if it's me doing the problem originally, but it's okay. It's not gonna take time. So it's gonna be dx multiplied by 15, dx multiplied by 15 minus 40 times 1 equals 0, and then I can calculate the virtual reaction dx equals 2.6 periodic, and if we do summation of forces in x, it's going to be equal to ax also. There you go. So we have the 3 reactions here, meaning this force here then has to be also 2.6 as well as this one, because it's the same one there, 2.6. And then if I do summation, I can go to this joint A, and if you go to the joint A, you have this force of 1, you have this force here of 2.6, which is the reaction, and then you're gonna have these 2, which is the AE virtual and AB virtual, AE and AB virtual. Now, of course, this force has to be in compression, and apparently this one is also in compression, but if you don't see it, you don't see it. It's okay, you don't have to do it. And remember, you have the same triangle, 3, 4, 5. So I can do here summation of forces in the y direction. So I have summation of forces in y here, and then I have this 1 minus AE multiplied by 3/5 equals 0, which tells me that AE is equal to 5 divided by 3, 1.6 repeated. Remember, we don't have units here, or we might have the same unit as the other unit, like kip, but I don't put the units here and I correct at the end. That's what I do. So 1.6, meaning this is 1.6, I mean AE, right? Yeah, AE is this one. 1.6, meaning this is gonna be also 1.6, and then I can do summation of forces in X equals 0 here. So if I do summation of forces in X equals 0, then you're gonna get 2.6 minus AE multiplied by 4/5 minus AB equals 0. AE is this value, so AB is gonna be equal, let me see, 2.6 minus 0.8 multiplied, 0.8 by the way is 4/5. Some people tell me, why do you put 0.8? 2.66666, and this was 2.6 repeated. Minus 0.8 times 1.6 is 1.3 repeated. So this is gonna be 1.3, which is gonna be 1.3, which is gonna be 1.3, and this is also 1.3. Now the only missing one is this one, and in order to do that, you can go to the joint C. 1.3, and then you have this force here acting in this direction, and this angle here once again is 345. So this force here, which is called CE, by doing summation either force in X or Y, let's do it in X or in Y, minus 1 plus CE times 3/5 equals 0. So it's going to be 5 divided by 3, meaning CE or EC, whatever you want to call it, is 1.6. And you can verify that. So now this force here is 1.6, and this one here is 1.6. Now, what we have so far is this. We have our virtual structure, we have our real structure. Based on those, what I like to do is I like to prepare a table, because what I have to do is apply the general rule or the general principle of virtual work. So I know that I'm going to need to multiply the small n meaning internal forces here, and big M means internal forces here, and divide that by each one of the areas and by E, and multiply by the length. So I'd rather doing this, and it's more organized if you do it. So I'm gonna put the member here. I'm gonna build a small table member, and then I'm going to put the length here. I'm gonna convert that in inches for unit coherence, and then I'm going to put the area, because as you can see the area changes in the different members in inches squared. I'm gonna put here the real force, which is called capital N, or P, the real force. And I'm going to put here also the virtual force, small n, or it's called also U, and this is the virtual force. And then I'm going to create because E is constant, I'm gonna keep it outside, this E. I'm gonna put that equation here. I'm gonna copy that equation here on top. So 1 times delta is gonna be equal to the summation of n times n divided by AE multiplied by L. This is what we have. So I have n, big N, small n, I have L, I have the area, and this E is constant. It says here, it doesn't change the material, so E is constant. So I'm gonna keep that E until the very end, at the end. And what I'm going to do is I'm going to multiply n times L divided by A. And I'm going to add all of these, and at the end, whatever I have, I multiply by 1 divided by E, because I'm not going to do that multiplication per every single member every single time. So I'm going to start member AB, BC, DE, what else? AD, BE, what am I missing? AE, and EC. I think that's the only thing that I'm missing. EC. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Good. So this is the table that we're gonna be building. Member AB, AB, AB. What is the length of this member? It's given. It's 20. 20 times 12, because I'm converting it into inches, 240 inches. And this is also 240, 240. AD is 15, 15 times 12 is 180. BE, 180 also. AE is the incline, this one. So the incline one is going to be 240 squared plus 140 squared. 240 squared plus 140 squared to the 0.5 square root 300, because this is the hypotenuse, right, the diagonal, and AC is the other diagonal, and it's also 300. Now the areas, you can read the areas from the information provided by the problem. So the area for AB is 4, and this is also 4 square inches, and this is 4, and 3, and 3. BE and AE is 3, and AC, no, what is AC? AEC. And you didn't correct me, guys. You should correct me. EC, so EC is 4 square inches. Now, I'm going to put the internal forces for the real structure. Look at that. But remember, you have to keep the signs. So AB, for AB is this one. It's 33.3 in compression. So put the negative sign as compression. And one of the things that I really advise you to do is, if this is periodic or repeated, put that, all the decimals that you can put in the calculator over there. So once again, this is also BC. BC is the same, 33.3 in compression. Now DE, where's the E? Where's the E? 100 here, tension. And then AD 50, BE 25, AE 83.3 in compression, and easy boy 41.6 here. Okay, and now we go and we do the same thing here for the virtual one, and we start AB negative 1.3, BC negative 1.3 also, DE 2.6, AD 1, BE is a zero force member, AE is this one, 1.6, but it's negative in compression, and EC 1.6 right there. Now what do? We multiply this times this times this and divide by that. That's what we do. By doing that, this is gonna be 2666.6. Same thing here. This is gonna be 16,000, 3,000. This is 0 because this is 0. This is 13,888.8, and this is 5,208.3. Now what do we do at the end? Summation, summation, summation. That's what the equation says, right? Summation. We add all of those, and that's gonna be 43,430. And then I get this value and multiply by 1 divided by E, and the result that I'm getting will be this. So delta is going to be equal to 43,430 divided by E, which is 29,000. And then if you check the units are going to be coherent, because this is going to be all in inches and kip, and this is also KSI, so the final result is going to be in inches, which is what we're looking for, and this is 1.5 inches. 1.5 inches. Now, this is what the problem is asking us. Determine the deflection of the point C due to those loads. Repeat the procedure. Do statics in the real structure and calculate all the internal forces. Do static in the virtual structure by placing a unit load in the direction and in the point that I want to determine the deflection. Apply the virtual work equation, external work equal to the internal work, build a table, and calculate the result. Now, just an idea for the end. You have here 1.5 inches, and this is a positive, right? However, look, the deflection that we thought, we put a unit load pointing downward here, meaning this is a 1.5 deflection downward in the same direction that we put the deflection here. If I got a negative value, and originally I assumed this going down, that will mean that the deflection will be pointing up and not down. But because it's the same sign as the direction, it's the same sign, is positive, that means that the deflection goes in the same direction that I put my virtual load. I hope that you like this video, guys. Keep watching, and I'm gonna create now a couple of extra videos in the fabrication defect and also in temperature change. See you next video. Bye.